What's going on, guys? Andy here. We are continuing the From Zero to Hero journey with a special problem which I think is the perfect introduction for you guys who are beginners at the dynamic programming approach chapter and want to learn more about this. So we are going to see how to approach these kinds of problem. I'm going to give you a bulletproof formula for solving these kinds of problem, and we are going then to write the code together. So stay with me, guys, it's going to be awesome. Consecutive subsequence is called. And let's read the statement together. You are given an integer array of length n, and you have to choose some subsequence of this array of maximum length such that this subsequence forms an increasing sequence of consecutive integers, right? So in other words, the required sequence should be equal to some x, x plus 1, dot dot dot, x plus k minus 1 for some value x and length k. So, first of all, what is a subsequence? A subsequence of an array, as they say, can be obtained by erasing some, possibly 0 elements from the array. Then, you can erase any elements, not necessarily going successively. The remaining elements preserve their order. Alright, this is important. For example, for the array 5, 3, 1, 2, 4, the following arrays are subsequences. 3, 5, 3, 1, 2, 4, like the whole array, right? 5, 1, 4. 1, 3 is not. Because if you take 1, 3, 1 is at position 3 and 3 is at position 2, and you can't swap the positions. You have to maintain their order. Super important. So, let's take a couple of examples to understand better the statement, right? So, again, very simple here. I'm going to take my notepad. I'm a classy guy. And let's take this array. 3, 3, 4, 7, 5, 6, and 8. Perfect. Well, the answer is 4. So the length is 4. And it looks like their subsequence is formed by the positions 2, 3, 5, and 6. So, at position 2 we got a 3. At position 3 we got a 4. At position 5 we got the value 5 actually. At position 6 we got the value 6. So 5 here and 6 here. Alright, so as you can see, this subsequence is basically a subsequence of values which are increasingly and consecutives, right? 3, 4, 5, and 6. Right. For the second example, if you take a look at this array, which is 1, 3, 5, 2, 4, 6, 1, 3, 5, 2, 4, 6, the solution is 2, and it's only formed by the positions 1 and 4, right? So value 1 at position 1 and value 2 at position 4, right? So this is the answer. All right. Now, you know what is a subsequence. You know that the elements should be increasing and consecutive. Let's think of some brute force approach. But first of all, I'd like you to notice that when we want to find this subsequence, right, a subsequence formed by increasing consecutive integers, this subsequence always has to end somewhere, right? It has to end at some position. So, we are going to solve this using dynamic programming approach. And, very important, the step 1 when solving each dynamic programming approach, I'm going to write it here. The step 1 is to figure out what is the information you want to hold, right? So, find out the information you need. Usually this information is going to be stored in memory using arrays, right? Could be 1-dimensional, 2-dimensional, 3-dimensional. It's just based on the complexity of the problem. So, we are going to start here easy because we just have an array which is 1-dimensional. So we are going to have here dp of I, right? It's an array, only 1 dimension. And what should be this answer, right? This is the most important question. Well, let's think about this. If I want this subsequence, it obviously has to end somewhere. So I'm interested in what is the last position of this subsequence, right? Where does this subsequence end? So let's say dp of I. Right? Always you take those parameters that you need and put it as dimensions in the array. So dp of I is going to be basically the statement of the problem. So the max length of some valid subsequence, let's say, right? Which ends in position I, right? So it ends at position I. Perfect. Step 1 is now done. We know what we need to compute, which is awesome because if we manage somehow to smartly compute this array, what is going to be the answer of the problem? Well, this is the step 2. Step 2 is figuring out if you know how to solve this array, it's not going to be useless. So you know how basically to get the solution of the problem. And it's pretty standard, right? Because for the length, you are going to take the maximum between dp of 1, dp of 2, dp of 3, and so on until dp of n, right? Because your subsequence could end at any position. You take the maximum out of this. Perfect. Now, step 1 done, step 2 completed. It's time for step 3. We know what we should compute. So the step 3 is obviously how to compute it, right? So step 3, right? So step 2, let's right here, is find out the answer, which we know is going to be this one. Perfect. Now, all right, for step 3, we need to find out how to compute the dp. And for this, we are going to need something that's called the recurrence formula, I think, something like that. Okay, so dp of I. The recurrence formula is based on the following thing. You want to compute this information, this current state, which is dp of I, using states that were already computed in the past, right? So let's say I want to compute this array starting from position 1 all the way to position n. When I want to compute dp of I know that I've already computed dp of 1, dp of 2, ... until dp of I minus 1, right? So I want a formula based on those values that are already computed. And let's think it like this. When I have dp of I basically know in what position my subsequence would end, right? So let's take our example of 3, 3, 4, 7, 5, 6, 8. And let's say I want to compute, I don't know, dp of 6, right? So when I want to compute dp of 6, let's take a look at position 6. Position 6 is this element, which its value is 6. So I know that if that's the last element, the previous element has to have a value 5. And its position is going to be on my left, right? So I can try out every position, starting from position 1 all the way to position I minus 1. And if that element has a value which is my value minus 1, that means it's a possible previous element for my sequence, right? So for dp of 6 in this example is going to be dp of 5, because that value 5 is at position 5 plus 1, right? Because a of 5, as we said, is equal to a of 6 minus 1, right? So the general formula is dp of I is going to be some dp of j, right? Some position plus 1, where, very important, a of j is going to be equal to a of I minus 1, and 1 is less or equal than j, 1 less or equal than j, which is less than I, right? So, perfect. Now we have a recurrence relation. We can make a for loop and try each of these j's from 1 to I minus 1, and for each valid one, we can update our dp. So, dp of I, as we said, from all our j's, what is going to be, like, we can have multiple possible valid j's, right? And for each j, its formula is dp of j plus 1. So what should we choose between all these options? Well, what does our problem ask us? For the maximum length. So we are going to choose the maximum value from all these possible values, right? So I'm going to have here maximum between dp of j, right, with 1 less or equal than j less than I, and a of j is equal to a of I minus 1, everything plus 1, right? Because that plus 1 is a constant, we need to take this max dp of j for all the valid j's. Perfect. Now we know how to compute our array. Step 4 is basically very tight to step 3, because we need to know in which order we will compute these dp's, right? And how we know that is super simple. We look at the recurrence relation and we see that, okay, in order to compute my dp of I see that I need the maximum between dp of j's, where j is between 1 and I minus 1. So I need to have computed already all the dp's with positions on my left. So find out the order in which you compute your information. And this order is going to be starting at position 1, going to position 2, 3, and so on until position n. So my order is going to be dp of 1 first, then dp of 2, then dp of 3, and so on. And when I should compute dp of I, let's say I got everything that I need. Perfect. And I got a step 3. recurrence relation, I got a step 4, the order, which is perfectly. You compute the array and you have your answer. Now, what is the time complexity of this algorithm? Well, let's think it like this. For the time complexity, we are computing n values, right? So we are computing n values, or how I like to call it, n states, right? So values or states. Perfect. Now, for each state, in order to compute it, we look at the recurrence relation and we try each j out. So we are making a for loop, right? So basically, what do we do here? Well, first of all, I got this for loop with I starting at position 1 less or equal than n I plus plus. And when I want to compute, so for computing dp of I make another for loop, right? So for int j equals 1, j less than I, j plus plus, and if this a of j is equal to a of I minus 1, what do? I update my dp of I. dp of I is going to be the maximum between what it already was and this new possible value, which is dp of j everything plus 1, right? So it's pretty obvious that we have two nested for loops. This is a brute force approach, guys, and its complexity is big O of n squared. But we still have something. We have a brute force approach. And from this approach, that's why I love to start with brute force approaches. They are super amazing because most of the times you can start from there and figure out, all right, I just need to do that and I'm gonna have the perfect approach for the problem. So let's think about how to optimize this, because the optimal solution is going to be big O of n, right? This is why you have in the restrictions, if you check those out, n less or equal than 2 cross 10 to the power 5, right? Because you need linear solution. So, optimal solution big O of n. We are going to take the fundamental solution for the brute force approach, this dynamic programming approach. But we are going to be smart about it, and we should break it down to two things. Why is my complexity big O of n squared? Well, it is because I have to compute n states, and for each state, I got a big O of n recurrence relation. All right, that was the word, relation, not formula. But it's okay. So I have n states, so n times I have to perform a big O of n recurrence relation. So in order to make this big O of n total time, I have two possible choices. First of all, I won't compute n states, I will compute only one and perform a big O of n recurrence relation for that, right? So I can have one state crossed big O of n relation, recurrence relation, and this is a big O of n, or I can have n states and a big O of 1, a constant time recurrence relation. Those are my possible options. Now, for the first option with one state, that's not quite smart. And that's not quite possible because I have to try each position out. So for my subsequence, I need basically to fix what is the last element of this. So I can't just guess, okay, it's going to be these positions, that's the one. I have to basically go and try each position out, right? So n states is going to remain there. But can I be smart about it and make it from big O of n to a big O of 1 recurrence relation? And I can. And how to do that? Well, let's take a look at my recurrence relation. It's the maximum between this dp of j's with j from 1 to I minus 1 and a of j is equal to a of I minus 1. So, what do I need to know really fast? I need to know the maximum between all these dp of j's that I have already computed, right? Because when I am in this for loop, in this first for loop, when I am at step I have already computed everything between 1 and I minus 1, right? So I have gone through all my possible j's, through all my possible dp of j's, but I'm going to need here the maximum between all of this, but with the property, only those with the property that aj has a special value, and that value is a of I minus 1, right? So, the following idea comes to my mind. I should have somehow pre-computed means before I even perform this recurrence relation, I should have an information like this. I should have another array max dp. And max dp should mean max dp of some x, let's say, is going to be the maximum between dp of j's with the property that a of j equals x. If I can compute and have fast this information, I'm done. Because the maximum between, so as we said here, dp of I is equal to the maximum between dp of j, or everything plus 1. Perfect. But this maximum between this dp of j's is now going to be max dp of, and you guessed it, a of I everything minus 1, right? So I'm taking this dp of j's into consideration, I'm taking their maximum and then add 1. I only need to have computed this array. And this array is going to be computed along with my dp, right? Because basically this array is computed using the dp's. So along when I compute the dp array, I will compute this array too. And let's think about what is going to be its formula. So how this array is updated. Well, if I take a look here in this main for loops, right? Well, when I am in this for loop and I finish computed, right? Let's say here I have finished computing my dp of I, right? I have finished computing it. It's done. I know its value. When I know its value, I should update my max dp array in order to use it for my further steps. So, max dp. Well, what is the new thing here? When I computed the dp of I, right, I have this new value which could affect my array max dp. But where can it do this? Well, max dp of x is the maximum between dp of j's where a of j is equal to x. So I need to go to this value, to my a of I here. And at this position, I should update the max dp array in case this dp of I is greater than what already was the value in max dp. So max dp is now the maximum between max dp of a of I and dp of I, right? Does it make sense? It should does, right? It should do. Because now I know the max dp. So when I have finished computing dp of I update my max dp array, which can only change in the position a of I. And now I can go here in this for loop for j and remove the for loop, because what do I do now? I know that dp of I is equal to what? And I want to pause this video and think about what should I write here. After you did this, it's max dp of, well, my a of j should have been equal to a of I minus 1. So max dp of a of I minus 1 plus 1. So now I can compute this dp of I. This is big O of 1. This is constant time. And after I do this, I can update my max dp array still in constant time. So this is big O of 1 too, which is super amazing, guys. I have only one for loop. I have extra memory because I use an extra array, which is max dp, but I can know what is the value of dp of I in big O of 1, and I can update my max dp for further use, for further computing my dp's in big O of 1. And this is how we get the solution in big O of n, guys. Now, let's think about our output. We should output the maximum length, and furthermore, we should output the position of our optimal subsequence. Well, how do we do that? The maximum length, what do we set? That the answer, look here, is going to be the maximum between dp of 1, dp of 2, dp of 3, and dp of n, right? So let's assume that when we computed the answer, this answer is some dp of p, right? So at position p, we have the maximum dp value, and this is the answer dp of p. So we print dp of p, everything is okay, but we still need to print those indexes. And in order to do that, we are going to need one more information, and that is, okay, I know what is the last element, right? I know my subsequence ends at position p, but what is the previous position from this solution? I should know that. And I can only know that while I compute dp of i's value. So we will have another extra array, which is going to be the previous element. So my arrays will be dp of n max, right? Max dp of n max, and I'm going to have another array which is going to be, let's say, previous element of n max, right? And think about this. When I compute dp of I is max dp of ai minus 1 plus 1, basically what do I do here is I take that j, that previous element's position, and then I add my position too, right? So I should know that j. Well, in order to know that j, in my max dp, I know the value, I know the maximum value. I should know what is the position for that maximum dp value that I'm looking for, right? I'm not going to need only the value in order to know the dp. I'm going to need the position too in order to know the prev element. So what I can do here basically is change a little bit the meaning of max dp. So here, max dp of x, right? Let's take it from here and put it right here. Max dp of x, instead of being the maximum dp of j with aj equals x, which is good, let's change it from being the value to being the position. So let's change it to be something like this, to be that j, right, some j, where a of j is equal to a of I minus 1, obviously, right? And that j has the maximum dp of all. So this dp of j is actually the maximum between all these dp of j's, let's say, right, with this j. So all this dp of j, let's say j prime, all right, j prime, where a of j prime is a of I minus 1, right? So what I basically did here is, instead of holding the value of that dp, we now hold its position, right? Perfect. Now when we know this position, dp of I is not going to be max dp of a of I minus 1. This max dp is now going to hold us the position. So in order to get the value, to get the dp from that position, we will need dp of this max dp. Perfect. Now we have computed the dp. After that, we need to update our max dp. But it's not anymore the maximum between what it was and dp of I. I need the position, right? So if this value dp of I is actually greater than what was the value of the max dp, my current max dp, so dp of max dp of a of I, right? If now I found a greater value, this is perfect, because I can say that max dp of ai is going to become I, right? So the position with the greatest dp of I, which is valid for the value ai, is now going to be I, which is perfect. And pause the video now and think about what is going to be the value of prev element. What is going to be its value? Prev element of I is going to be equal to max dp of a of I minus 1. So max dp of a of I, everything minus 1, right? This is going to be the prev element of I. So we have computed our dp, taking the position from max dp of a minus 1. We have computed the previous element, taking the position from max dp of a minus 1. We have updated our max dp. Perfect. We have everything that we need here now. And this is it, guys. We know how to compute the answer. We know now how to build our answer subsequence, everything in linear time, and we basically solved our first dynamic programming problem. It's not an easy one, but it's very nice for the introduction because it has a lot of concepts, right? So we're starting from the brute force approach, we are going to a linear time approach, and we even find out how to build that subsequence. The code for this problem is going to be great. It's going to be interesting, and you are going to learn a lot of things from it. So I'm very excited. I don't know if I should keep it for tomorrow or for today, but please, if you like this video, subscribe to this channel, hit the like button, and let's say at 50 likes, we are going to post the implementation for this problem. I know it's cheesy, I know every YouTuber does that, but you are definitely going to take a lot of value from the implementation. So, really hope that you understood the problem, really hope that you enjoyed it. Don't forget to join our Facebook group, in which I will post along with my moderators challenges every day, or bits of wisdom, or maybe something from our experiences in competitive programming or interview questions. And we are going to grow as a big community and sharing ideas all around the world maybe. This is the point. And again, this was Andy. I hope that you enjoyed the problem, and I will see you in the day 3 of From Zero to Hero journey. Bye.